Hi, welcome to my channel Easy Aviation. Here we discuss about the small short topics about the aviation field. Today's topic of discussion is measurement of airspeed of an aircraft. This is definitely an interesting topic. So I'll start with a very basic equation that is known as Bernoulli's equation. Equation states that the pressure energy plus the kinetic energy plus the potential energy of any system is constant. So as you can see in the system, there is a energies at point 1, there is another energy is point 2, and the total summation of the energy at both the point will be a constant. So another interesting fact, that if a fluid is flowing, that the velocity of the fluid is less than 0.3 Mach, then the density at point 1 will be equal to density at point 2, and these fluid are known as incompressible fluid. Incompressible fluid. If the velocity is greater than 0.3 Mach, there will be definitely, because of the friction between the fluid layers, there will be definitely a density change, and those fluid density 1 will not be equal to density 2, and they are known as compressible fluid. So in field of aviation, when the aircraft is flying in straight and steady flight, the change of the potential energy is very less, so we generally negate this term. So this equation reduced to pressure energy plus the this is rho density, half rho v square will be constant. In the so when we again discuss about this equation, this pressure is the static pressure or the pressure which is around the aircraft, denotes by P. This is the dynamic pressure or the because of the kinetic energy. So when the aircraft is moving in the forward direction, there is a velocity because of which this pressure energy is there, and the summation of both of them, that is constant, which is known as total energy. So in any case, the total energy will remain constant. This is summation of the static pressure and the dynamic pressure. So if the aircraft is not flying, if it is static, at that time the static pressure or the pressure of the atmosphere surrounding will be the maximum, and as soon as it moves, the static pressure started reducing and the dynamic pressure increased, then the summation becomes the total pressure energy of the system, rather total pressure energy of the system, because this is also stated as a dynamic pressure. Okay, so why this equation is important, I'll be explaining in the next page. So here I have taken a pictorial representation of a airspeed indicator. So how a airspeed indicator work, I'll explaining in this. So as I've discussed, this is the pressure energy, and this is the this is the static pressure, this is the dynamic pressure, and this is the total pressure. I'll write it as P naught, which is always constant in a flight. So pressure energy, since it's a static pressure, this is dynamic pressure. Okay, so when this is how the exploded view of a airspeed indicator. This is a pitot static tube. Generally have seen in front of helicopters, aircraft, there are tubes, small tubes, which actually measures the which actually allow the air or the free stream of the air to go inside, and there are dots, or there is a static port which are also available, which measures the pressure of the atmosphere. So as you are aware, at the ground level the pressure is different. As we go up, pressure reduces and the density reduces. So these holes, these pitot static tube, this measures the pressure at different heights. So as you can see, this is a pitot tube which measures the dynamic pressure plus static pressure. So because of the flow which is going inside, it measuring both dynamic pressure, that means the total pressure it is measuring, and it is going inside the tube, inside the bellow. As you can see, I am marking it. And this is a static port, which is just in a fuselage. I'll just draw. In a fuselage, there is a small dot or a small hole which is connected here in this line, and this pressure is connected in the chamber. So what you see, that in the dynamic pressure, so in the bellow, there is a summation of static pressure and dynamic pressure. However, in the chamber there is only a static pressure. So this both negates, and only the dynamic pressure is left inside the bellow. I hope you have understood this. Bellow. So I'll take another color. I'll take this blue. So this blue I am marking is the total pressure, which is the summation of static pressure and dynamic pressure, and outside this green part, this is only the static pressure. So static pressure from outside and dynamic static from inside. So only the dynamic pressure is left, which is acting in the bellow. So now with the as you can see, there is a mechanical linkages. So this dynamic pressure is corresponding to the indication. With the help of the mechanical linkages, the bellow is either increase or decrease as we go up or down. Since we are going up, the pressure and density reduces, so the bellow reduces, and depending on how much reduction is there, it will gives the indication on the airspeed indicator. Okay, so now the interesting thing comes. I'll take another page. So as I said, airspeed indicator, the indicator is corresponding to the dynamic pressure, which is half rho v square, which I have already discussed in the previous. So the indication which is coming on the airspeed indicator, okay, corresponding to the value of half rho v square. So this value which is showing on the indicator is known as instrument indicated speed. Instrument indicated speed. So if there is an error which is inside the instrument and which has been conveyed by the manufacturer that there is some error, if that error is removed from the IIAS, that is instrument indicated airspeed, that speed is known as indicated airspeed. Okay, now from indicated airspeed, if we remove the position error, position as in the aircraft is there, okay, there is a pitot and there is a static tube, but because of the air flow, this static tube sometimes doesn't measure the exact pressure of the atmosphere. Rather, it is varied because of the airflow or because of the position of these static holes. So these kind of error is also provided by the OEM or the manufacturer. And when the error, I'll just write error because of position, if that is removed, that speed is known as calibrated airspeed. From calibrated airspeed, if we remove the compressibility error, so what is compressibility? Because of the velocity, compressibility error, because of the velocity of the flow. I have told if the velocity is more than 0.3 Mach, which is generally is, there is a density change. So if those errors are removed from the indicated airspeed, that speed is known as equivalent airspeed. So equivalent airspeed, calibrated airspeed, indicated airspeed are the errors which has been removed from the instrument indicated airspeed, which is the raw airspeed which has been indicated on the ASI, and that is corresponding to the dynamic pressure, half rho v square. So now half rho v square, point to note is that density which is implied in this equation is a constant term. So the speed which is visible on the ASI is the multiplication of these. Half is constant, rho is taken as constant, which is equal to 1.125 kg per meter cube. That is ISI condition, and which makes it this as constant. So velocity measured of the aircraft is equivalent to, but when the aircraft goes up in the air, the density reduces. So this factor also needs to be incorporated into this. So I'll take a fresh page, I'll explain what is happening. So this aircraft is flying at particular altitude, let's say 10,000 feet. So at this 10,000 feet, the calculation will be equal to half rho v square. That is, let's say if the density we have taken as the true density which is there at 10,000 feet, the velocity, let's say it is a true speed. If we take another case, let's say at 10,000 feet, if we are taking the dynamic velocity where the density is taken as the basic density, that is 1.125 kgs, then the velocity is the indicated airspeed. So here we are trying to find the relation between the true speed and the equivalent airspeed, which we had discussed earlier. So if since at the height the speed which is showing, if we make a relation in both of them, then you will find that true airspeed, I will write v square ts as true airspeed square is equal to rho naught by rho t v indicated speed. Rather, I'll write v square. So remove the square, we'll write TAS, that is true airspeed, will be equal to 1 upon under root of rho true by rho naught and v I'll write indicated airspeed, IAS, or rather EAS. So this term rho by rho naught, that is true rho, that is the density at particular 10,000 feet, and the density at ground level, this is also known as rho, that's known as sigma, which is a relative density. So the relation comes out as the true airspeed will be equal to under sigma and equivalent airspeed. So whenever the aircraft fly as 10,000 feet, whatever the ASI is showing, let's say it's showing 100 knots, the true airspeed is very much higher than this, and that's true airspeed is generally shown by many equipment known as GPS, Doppler velocity sensor, inertial navigation sensors. So these are the electronic sensors which are showing you the true airspeed. However, the basic instrument which is always there in all the aircraft, that is indicated airspeed, which is measuring the speed depending on the velocity considering the density at sea level, which is actually not the right right calculation. So when you calculate the TAS, true airspeed, these from the equivalent airspeed, this is the formula, which is very important formula, and TAS will always be higher than the equivalent airspeed when we go up in the height. So here I conclude the video. Thanks for watching. Please subscribe my channel for more interesting videos about the aviation field. Thank you.